So let's talk about the foundation of information theory and the main concept. So mathematically, the formulation of the entropy for the discrete variables will be hx equal to the negative value of the sum of the probability of an event multiplied by the log at the base 2 of that probability. And for the continuous variable context, we're going to use just the integral instead of the sum, because here we have continuous values. And these are two examples of coin tossing and dice rolling. You know, in the coin tossing, we have two possible outcomes. Okay? So if we want to measure the entropy, which is the number of bits that we need to have, and considering that we have independent events, the head and the tail are completely independent, we're going to have 0.5 probability for both. And calculating this expression of the entropy in the discrete variable use case, okay, we're going to have 1 bit. This will lead to having 1 bit. In the case of dice rolling, how many outcomes we have? How many possible outcomes? 6. So we're going to calculate this, the sum from I equal to 1 to 6, 1 divided by 6 multiplied by the log 2 of 1 divided by 6, and here it gives the value of 2.5258 bits. So here we have higher randomness because we have uniform distribution among 6 possible outcomes instead of 2 possible outcomes. And so this is highly random, and this requires higher, okay, bit encoding, number of bits to encode the information. So the information gain here is higher because we need to encode that in 2.58 bits because we have greater randomness and unpredictability. Now we talk about the conditional entropy and mutual information. So what is the definition here? Imagine that you have two random variables, x and y, and you want to calculate the conditional entropy. It's like we calculate the conditional probability. Okay, so the mathematical expression of the conditional entropy is hx given y, and will be equal to the sum of all possible values of x and y, the joint probability pxy multiplied by the log 2 of joint probability pxy divided by the probability of y. And so this is the equation for the conditional entropy of x given I know the value of y. And let's try to, okay, on the other hand, the mutual information, it's like the joint probability, which is equal to I, x, and I. So this is the information of having both the joint event, and this equal to the sum of pxy, the joint probability, multiplied by the log at the base 2, the joint probability of pxy, divided by marginal probabilities of px and the marginal probability of y. And this can be expressed as ixy equal to hx minus the conditional probability, conditional entropy of x given the y. Now let's try to understand this based on the example. Let's assume that x and y are completely independent. So this means the joint probability is equal to the product of marginal probabilities. This is known in probability, okay, the joint probability. And let's assume that px is an array of 0.5, 0.5, and the same for y, it's an array of probability 0.5 and 0.5. So if I calculate the joint probability using this formula, we're going to multiply 0.5 by 0.5, so we're going to find 0.25, 0.25, and 0.25, 0.25. This represents the joint probability over here. So now I can calculate this conditional probability, which is equal to joint probability that I have here, multiplied by the log of joint probability divided by the probability of py. So look at this picture. Now, if I calculate the entropy, because I have all of them are 0.5, it's completely random. So the entropy of y alone will be equal to 1. Already calculated. This is like the coin tossing. And then the conditional entropy of h, y given x, it's equal to 1. Why? Why it is equal to 1? It is equal to the same as hy, because x and y are independent. Okay? So if you know X, you don't have any information about Y. They are completely independent. And this is why the joint probability is 0. Or, sorry, it's not the joint probability. The mutual information is 0. Okay? Because here, look now, this is the log of 1. This divided by this is equal to 1. So the information will be 0. They are independent. Okay? It means the knowledge of one variable doesn't give any clue about the other variable. They are completely independent. Does it make sense? Okay, so this is the mutual information. Okay, the mutual information is equal to 0 when the two variables are completely independent. Now let's consider some kind of dependency between X and Y. And here we're going to assume the joint probability equal to 0.3, 0.2, and 0.2 and 0.3. And we can calculate Py as the sum on the x-axis. Okay? That will give the marginal probability of Y. Now, calculating the marginal probability, so it will be 0.5 and 0.5. In this case, we will have the entropy of Y is equal to 1, because we have 0.5 and 0.5. Now, if we look at the conditional entropy here, okay, the conditional entropy will be slightly smaller than 1, 0.971. So what does this represent?
There's some dependency.
Because there is some dependency, so we have less uncertainty. Okay, the knowledge of X will give me a slight information about what could be Y. Very small information, but it's not completely independent. Okay, so you can see that the conditional entropy here is slightly smaller than 1 because there is a small dependencies between both of them. Okay, so we can see it's close to 1. And now the mutual information is not 0. It's something around 0.029 bits. And because we have some dependencies between both, and this value is just 1 minus this value, okay, which represent the mutual information gain. Okay, so this gives you a little bit of understanding about the relation between dependent variables, and now when we do prediction, the variables must be dependent. And if they are not independent, if they are completely independent, it means in our case of data science and predictive model, X is not a feature that will allow to predict Y. And if there is some kind of dependencies, there is some entropy, in this case, we can consider X as a feature. And now we're going to say, okay, at which level that we are going to consider X as a feature. If there is a little bit of dependencies, maybe it's not relevant. And this will depend from your data set about and the feature reduction problem. Okay, so we need to reduce the features so that we consider those that will bring more information that will impact the outcome of the predictive models. Does it make sense?
Yes.
Okay.